Hello everyone, I'm Devinder Kumar. So welcome to this lecture series on the applied chemistry topics. So I'll be discussing about electrochemistry. So starting with the what are different kind of conductors, different kind of conductance, and then how the ions move through the solution, and slowly moving into the transport number, and later on describing what are the different type of electrodes in the that are used in the potentiometric titrations. So let's start. So what is electrochemistry? So electrochemistry is that branch of the science which deals with the study of electric changes in the electrical properties of the electrolyte and the chemical changes associated as the electricity is passed through them. So because the electricity is passed, there kind of certain decomposition reaction can take place, evolution reaction at the different electrodes can take place, and those will involve some changes in the electrical properties which are measured. So that's what electrochemistry consists of. And so what is electrical conductance? So substances which allow the passage of current through them is known as are known as conductors, and we uh, categorize them into two categories. One is metallic conductors, second one is electrolytic conductors. So what are metallic conductors? Metallic conductors are those conductors in which conductance happens because of the free electrons in them, mobile electrons in them. So for example, we can take any example of the metallic conductor from our standard uh, plus 2 plus 1 we have studied. So for example, sodium metal, potassium metal, so these are all metallic conductors. And since the electron is due to the movement of electron there, it is they are also known as electronic conductors. So and the second one is electrolytic conductors. So in these kind of substances, they conduct electricity in the fused state, molten state, and in their when present in the solution, when in the dissolved form, right? So and why do they conduct? There is a little bit uh, change in the mechanism of conductance. In metallic conductors it is the free electrons. Over here their molten or aqueous solution uh, conducts the electricity, and that is due to the presence of cations or anions, right? Because they furnish ions, they produce ions in the solution because they get dissociated once they are dissolved to a certain extent. We will talk about that on the next slide. So this is so electricity is conducted uh, conducted due to the different kind of ions produced by these substances, and those are called electrolyte, and these are called electrolytic conductors. And example can be molten or aqueous solution of the sodium chloride, sodium hydroxide, etc. So what are strong electrolytes? Those electrolytes which are when dissolved are completely dissociated in their aqueous solution, right? Or since they are completely dissociated, and hence they offer a large value of conductance, right? So the examples are hydrochloric acid, nitric acid, sodium hydroxide, potassium hydroxide, sodium chloride. Okay, and what are weak electrolytes? So let me just emphasize one more point. In the strong electrolytes, the dissociation is near almost 100%. Right, so those are your strong electrolytes, and weak electrolytes are those electrolytes where there there exists an equilibrium between the undissociated form and the dissociated form of the electrolyte, right? And they do not completely undergo dissociation once they are in the dissolved state. In they are dissolved in the uh, any kind of um, solvent, right? So an example is acetic acid, formic acid, ammonium hydroxide. So shown here in this slide is on the right is the conductivity cell, which measures the conductivity of a solution, and how this is measured and are related to conductance. Let's discuss that. So we all know that relation R is equal to rho L by A, where R is resistance, rho is resistivity. For metallic conductor, we have discussed. L is the length of the metallic compound. A is the cross-sectional area. So what is conductance? Conductance is the reciprocal, just the inverse of the resistance by definition. So if we just put in that in that equation, 1 by R is will be equal to kappa A by L, where what is kappa? Kappa is the specific conductance or conductivity of the solution and is equal to 1 by R, 1 by rho, which is a resistivity. All right. So this the units of G conductance will be 1 ohm inverse or the reciprocal of the ohms, right? And in the SI unit we also use Simon with the capital letter S as the units of the conductance. And what is A here? A is the this area of these two platinum electrodes for this cell, and L is the length between this separation or distance between these two electrodes, and kappa is the conductivity or specific conductance for this solution. So here is that relation R is equal to rho L by A, right? So once L is 1, A is 1, so rho is equal to R. So the specific resistance is equal to the resistivity of the material, right? For a sample of 1 centimeter in length and 1 centimeter square cross sectional area, which basically means you have 1 centimeter cube of the material, and reciprocal of the resistance, specific resistance rho is called specific conductance. Okay, so we just plug in that here. So R is equal to rho L by A. You just rearrange to get rho on the left hand side, which will be R A by L. All right. So 1 by rho is kappa. So L by A into 1 by R, that will be there. So 1 by R is just conductance. So kappa, which is specific conductance, will be equal to L by A into conductance. All right. So this is how these two variables are related for these substances. Conductance is equal, specific conductance is equal to L by A into conductance, and L by A is constant for a particular conductivity cell, because A is the area of those platinum electrodes, L is the distance between those two electrodes. So L by is constant. That's why this L by A is also known as sometimes we also call it as cell constant. All right. Okay, so this is specific conductance, how it is related to conductance of a solution we have just discussed. And from here you can also look at the units. So those are very easy. You can just derive it. All right. So what is equivalent conductance? Equivalent conductance is it is defined as the conducting power of all the ions produced by 1 gram equivalent of an electrolyte in a given solution. So basically, whatever the conductance is coming from, once 1 gram equivalent of that particular electrolyte is dissolved in the solution, that is your equivalent conductance. So how these are related, the specific conductance and the equivalent conductance? So let me just discuss once again. Specific conductance is what? It is the conductance of 1 centimeter cube of the solution, right? So the length separation between the two platinum electrode is 1 centimeter. Area of cross section for those platinum electrode is 1 centimeter square. So from that solution, whatever the conductance is coming, that will be your specific conductance. Now let's say in this 1 cc centimeter cubic of the solution, let's say we have 1 gram equivalent of the substance, our electrolyte. So basically then it will become, since it involves conductance of 1 gram equivalent, it will become lambda eq, equivalent conductance. And because it is coming from 1 cc, it is also specific conductance. So in this case, our conductance is equal to specific conductance kappa because it is the conductance of the 1 centimeter cube of the solution, and it is also equal to equivalent conductance because in that 1 centimeter cube we have dissolved 1 gram equivalent of the electrolyte, right? So what is molar conductance? It is the conductance of the ions, all ions produced by 1 mole of the electrolyte in the given solution, and mathematically it is related with the kappa as lambda m molar is equal molar conductance is equal to kappa by c, where c is your concentration taken in moles per meter cube in the SI units, and in the SI units for kappa will be Simon per meter, concentration moles per meter cube. So for molar conductance, it will be Simon per meter square per mole. Okay, so how does molar conductance varies with the dilution, right? So if we dilute a substance, what happens to the conductance? So shown here on this graph, what we have, we have plotted molar conductance on the y-axis, and on the x-axis is the square root of the concentration. And as you can see, as the concentration decreases to the left, let's discuss the acetic acid first. So there is a slight changes conductance as the concentration is decreased. Basically dilution is happening, you are diluting a acetic acid solution, and at very dilute solutions the conductance, molar conductance increases very rapidly. So what happens there? So since the conductance is increasing, this means number of ions are increasing. So what is happening for the acetic acid? Because as the consent it is diluted, a solution of acetic acid is diluted, and just recalling that acetic acid was the weak electrolyte, right? We discussed it under the category of weak electrolyte. So it is dissociated initially to a 5%, let's say, and as you dilute it more, its dissociation increases. So hence number of ions produced are more, and that is why this there is a sharp increase in the molar conductance at a high dilution. All right, so this is for weak electrolytes. Similarly, for strong electrolytes, for example H2SO4, you will also see a little bit increase in the conductivity, conductance, molar conductance at very high dilution. Similarly for the HCl2, but HCl and H2SO4, the strong electrolytes, are dissociated completely, right? So why still on dilution they show a small increase in the molar conductance, small as compared to increase in conductance of the acetic acid. So why is it so? The magnitude of increase in case of strong electrolyte is smaller for the molar conductance because they are completely dissociated initially. Only thing that happens on the dilution is that the ions are now more free to move. Their interionic interactions are less. Hindrance to their movement is less, and hence the conductance increases. So that's what we have in all in this graph, which is discussed right here, right? So, okay, so this is for molar conductance because it is depends upon just the number of moles what we have. Now, what will happen to the specific conductance? So, specific conductance, just to recall again, uh, by definition, it is the conductance of the ions present in the 1 centimeter cube of the solution. All right. So, whatever is there in 1 cc, and since on dilution you are increasing volume more, your concentration decreases, so number of ions per cc decreases. That is why specific conductance decreases, right? So specific conductance decreases, whereas molar conductance increases on progressive dilution. Okay, and for at any dilution, this from here we can also derive this degree of dissociation for weak electrolytes, lambda m by lambda m naught, where lambda m is the molar conductance for any concentration at any concentration, and lambda m naught is the corresponding conductance at the infinite dilution, and the ratio of them will give us by what factor the ions are increased. So that is degree of dissociation basically. All right. So now as the Ions are moving in the electrolytes once in the dissolved state or in the fused state. So let's define how they their mobility is there basically in their molten state. All right. So mobility, the conductance is due to their mobility. They are moving through the solution. So what are different factors that affect the mobility of ions, speed of ions in the solution? For example, molar conductance of at infinite dilution for HCl is uh, 3 times more than that of the NaCl. So they both have common Cl ion. It is just the cation that is different. So this means it looks like the mobility or the conductance of H ion is 3 times as that of the sodium ion, roughly only, right? So we here define a new variable here, which is ionic mobility, which is defined as the distance traveled by an ion per second under the potential gradient of 1 volt per meter. So what, how is ionic mobility defined? It is the distance traveled by an ion per second under the potential gradient of 1 volt per meter. Make sure we take 1 volt per meter because this is how in the SI units it is defined, right? So this is ionic mobility. So ionic mobility is much smaller for heavier ions, of course, because they move slowly, and is little bit is larger for the uh, lighter ions, and since they can move a little bit quickly. All right. So over here, the ionic mobility of H ion is found to be 5 to 10 times than that of the other ions, except hydroxide ion, which is I think twice or thrice. So mobility of H ion is found to be 5 to 10 times more than that of other ions, right? And why is that so? Because hydronium ion, H ion in the solution exists as hydronium ion, H3O plus, and that exists as a trihydrate of the hydronium ion, which has a structure like this. Okay, so this in increase in the mobility of H ion in the hydroxylic solvents only, right? So its movement is much better, much larger in the hydroxylic solvents for H ion, can be explained with the Groth's type mechanism shown on this slide here. By this mechanism, we know that H ion can form an hydrogen bond with the water molecule, right? And then, since let's say this H ion is the hydrogen bonded one, and now this H ion can easily be transferred to the next H2O molecule by the just the rearrangement of the hydrogen bond, and then further this H ion can be transferred to the can move to the next water molecule. So in this way, proton just hops on from one molecule to another molecule, right? And along this series of hydrogen bonded molecules, and that is what accounts for the high mobility of hydrogen ions in the water. And this type of mechanism is known as Groth's type mechanism. And in ice, the mobility of H ion is about 50 times more than the liquid water. So in ice, H ion moves 50 times more. The mobility is 50 times larger than the H ion in the liquid water only. Why is that? Why would that be? So we all have studied somewhere in the plus one, plus two, that ice has a nice cage-like structure in which molecules are, and a screenshot is shown here, and the molecules are very well tetrahedrally arranged here. Now, and in the ice at such a temperature, this there are less movement of these water molecules. They are almost locked, and in the this tetrahedral environment. Now the symmetry is such that this provides a fantastic movement from the for this H ions to move from one water molecule to other water molecule. And since the agitation within these different water molecules are less, and that's why this conductivity, this movement of H ions is much faster here. Right. So this was about for the movement of H ion in the water, which is little bit special. And now, if we discuss what are different factors that will define that will control this ionic mobility: size as well as charge. Right. If keeping that potential gradient as constant, size as well as charge will determine which ion will move faster, which ion will move slower. So if we compare lithium and sodium ions, which are from the same group, right, same group, so lithium ion both have the same charge, and out of lithium and sodium, sodium has a much larger ionic radii. All right. So it is that with the molecule, the ion, not the molecule, sorry, the ion with a higher charge density will have will be better hydrated because of the ion dipole interaction, right? So out of lithium and sodium ions, let's discuss which will have a higher charge density. Of course, for lithium, because it has a smaller ionic radii, and since charge for them is same, +1, right? Now that is why lithium plus will have a higher charge density, and it will be more hydrated. This means there are more number of water molecules around this, and hence once it moves through the solution, lithium ion will carry a larger shell of water as compared to sodium. So effectively it will become larger, heavy, the lithium ion, and hence the ionic mobility for lithium ion will be lower, of lower magnitude, which intuitively is reverse, because lithium ion is smaller. Oh, ionic mobility will be larger. No, ionic mobility is lower for the lithium ion due to higher charge density, right? Okay, and what is the effect of temperature? For roughly with increase in temperature, ionic mobility is increase, and that increase is 2% per degree in the vicinity of 25 degrees Celsius. So, what is the take-home message from till now? Can we explain growth type mechanism? And it is only for HN because it has a different special kind of mechanism by which it moves through the uh, hydroxylic solvents, right? So it is growth type mechanism for movement of H ions. Conductance and units, cell constant, how do we define it? What is the effect of dilution on molar conductance? It increases, but specific conductance decreases. So can we look at the mobilities order of H ion, lithium and sodium ion? Okay, so this is kind of exercise just to food for the thought. Let's move to the last topic further today, which is the migration of ions. How so we have just discussed that on applying electricity, ions moves. Can we show it? Can we visualize this? So Noyes came out with a very nice way of demonstrating that. So in a this YouTube, in these two limbs, what we have here is sorry, YouTube is filled with the 3/4 of the dilute solution of agar agar on both sides. Okay, and uh, all right. So what we have here is uh, up to the 3/4. Sorry. All right. So in this noise experiment, what we have is YouTube is filled with the dilute solution of agar agar containing KCl and a little bit of the phenolphthalein, which is an indicator we have used in the somewhere in the laboratory, right, of this applied chemistry. Okay, so and a drop of dilute solution of the NaOH is added to the right limb, and we all know sodium hydroxide, once we have once this basic solution goes into phenolphthalein, phenolphthalein will turn pink. So right side of the limb, this U tube will appear pink, right? And left side will appear colorless, and HCl is added because it's less than a pH of 8.2, which is the working pH range for the phenolphthalein, right? So now this limb is colorless, this limb is pink, right? So here sodium hydroxide is added, here HCl is added. Okay, let me move to the next slide, which here, all right. So so now this agar-agar solution is allowed to set into a jelly by placing in a ice bath for a few minutes, and a small amount of powdered charcoal is added here just to mark the boundary. So here and here a charcoal is added, okay, and a solution of HCl and copper chloride is gently poured very carefully over the charcoal on the right hand side. Here HCl plus copper chloride, and on the left hand side a solution of the NaOH is poured, and such that they do not mix very carefully. It is poured over here. So and here is the charcoal, right? So now we insert electrode here, and current is passed. So as the current, and this is given a negative bias, this is given a positive bias. So this is the cathode, so cations will move towards the cathode. This is anode, anions will move towards it. So it will repel what was here, if we remember, it was the sodium hydroxide solution. So and it will repel the anions and it will attract the H ions. So as the sodium hydroxide solution is there, hydroxide ion will move to this side, and remember phenolphthalein is here, and as this hydroxide will go cross this charcoal and go to this phenolphthalein, phenolphthalein will immediately turn pink, and the length to which up to which this pink color will appear will mark to the distance traveled by the hydroxide ion, which can tell you about its relative speed to the other ions, right? So on the left hand side the pink color will start to appear, and length will be proportional to the velocity of the hydroxide ion, and over here HN will start to move. And remember it was all pink here on the previous slide, but as the HN will move, it will neutralize the hydroxide, and immediately what will happen, the pink color will go away and it will become colorless, but it is blue due to the movement of copper 2 plus simultaneously. So the distance till which it is blue will mark the bound speed of the, will give us a estimate of the copper 2 plus, and the distance to which it is colorless will give us the relative speed of the HN. Now we can clearly see it is colorless to a the length for the colorless form is larger than the blue form. So this means which ions move faster? HN, of course, as compared to cuprous ions, sorry, cupric ions. And over here on the left hand side, for the hydroxide, the pink color will tell us the distance traveled by the hydroxide, or roughly give us the distance velocity of that pink ion. So in this, by this clearly by this method we have seen that this turns pink because of the migration of OH ions, mobility of OH ions. So ions are basically moving, and we can actually, we cannot see the really the ions moving, but we can visualize those. Okay, since the change is occurring, these ions are moving. So this is the noise experiment, right? So today we will just stop here, and thank you very much.